AP Review Lesson 4. In this lesson we'll take a look at some free response questions involving molarity and precipitate reactions. So this question says we have 3 beakers. Each of 3 beakers contain 0.1 molar solutions of one of the following solutes: potassium chloride, that's KCl, silver nitrate, that's AgNO3, and sodium sulfide, that's Na2S, 2 because you have +1 versus -2. The 3 beakers are blended or labeled randomly as solution 1, 2, and 3. Shown below is a partially completed table of observations. So take a look at this table. And what we've got is between solution 1 and 1, obviously it's the same solution, nothing will happen. But in the other 3 cases, we've got a black precipitate. When you put 1 and 2 together, we have no reaction when you put 2 and 3 together. So, and we're asking to give essentially the identity of these different solutions. So it says write the chemical formula of the black precipitate. Now, if we were to mix silver nitrate and potassium chloride, would there be a precipitate? And there would be. Silver chloride would actually precipitate because chloride is a robber of silver. If we think about the same thing here, this would also precipitate silver. Sulfides in general are not soluble, and silver sulfide is not soluble, so you got yourself a precipitate. In the final case, when we mix these 2 together, there actually is no precipitate, so no reaction, because both potassium sulfide and sodium chloride are still soluble due to the fact that they're both from group 1, and all group 1 metal ions are always soluble. So knowing that there's no reaction between these 2, what we can say is that the solution is between solution 3 and solution 2, between there is no reaction, are going to be KCl and Na2S, which means solution 1 must be the silver nitrate. In other words, this has to be silver nitrate. That's kind of a process of elimination. See if you can think through that one more time. And now furthermore, we can try to find out which formed the black precipitate. So between these 2, silver chloride and silver sulfide, if you had to guess, think about which you would guess would be the black precipitate. And your guess is right. The black precipitate is going to be the silver sulfide. Sulfides are going to be black. Chlorides are for the most part white. So knowing that this is your black precipitate, and the precipitate came from Na2S, we've already identified silver nitrate as being solution 1, so the one that forms a black precipitate is with solution 2, which means Na2S is solution 2, which means KCl must be solution 3. So that's how you would go about it. And now we can write the chemical formula of the black precipitate. And the black precipitate, here it is silver sulfide. And here it says describe the expected result of mixing solution 1 with solution 3. Well, solution 1 is silver nitrate, solution 3 is KCl. We should expect a precipitate to form. And you can say white precipitate if you want, but I would say just a precipitate would form. Don't give any extra information if you don't know it. So a precipitate forms is sufficient. It answers the question. Identify each of solutions 1, 2, and 3. So now we can say 1 is silver nitrate, 2 is sodium sulfide, and 3 of course is potassium chloride. So a simple free response style question using precipitates and solubility. Let's finish up with this question. One of the testing solutions often used in laboratory is this sodium hydroxide. You've actually used sodium hydroxide quite a few times. Describe the steps for preparing 100 milliliters of a 1.0 molar sodium hydroxide solution from a stock solution. A stock solution is one that was prepared and the one that we know the molarity of, using a 50 milliliter burette. Remember, a burette is what we used for titrations. It can dispense precise amounts of volume, precise amounts of solution. a 100 milliliter volumetric flask. Now these are the flasks that are used to prepare solutions with a little marking on them. So for example, you could say 500 milliliters on them and so forth. These are volumetric flasks. DI and a small dropper. And the dropper, if you want, I can draw a little dropper for your visual pleasure as well. So this little dropper comes out the water. And so we're asked to describe some steps. Well, first of all, let's find out the molarity, I'm sorry, not the molarity, but the amount that we would need to form a 1 molar solution. So because we're beginning with a 3 molar solution, and we want a 1 molar solution, 100 milliliters of it, remember molarity is moles per liter, so our molarity here, our beginning molarity is 3, and we want 100 milliliters, so we want 0.100 liters of the solution. So solving for moles, moles is just molarity times liters, which gets us 3 times 0.100, which means that we need 0.3 moles of the solution. Now, the question then is that we need 0.3 moles. How much of the 3 molar do we take out? Well, let's see, 3 moles of 0.3 molar. Let's rearrange the equation to solve for liters. Liters, remember, is moles over molarity. And so we got 0.3 moles divided by molarity, which in our case is 3 molar. So actually we need we went wrong somewhere, did we not? I know where we went wrong. Flip back a little bit. I substituted the wrong molarity. It is a 1 molar that we need, so this should have been 1.0 molar. Which, this would be a 1, which gives us here a 0.1. Which this becomes a 1, there we are, a little better. 0.1 divided by 3, which is, still 0.0333, so a third of a tenth, essentially. Here's how many moles we need from the original solution. I'm sorry, not moles, this is how many liters. Alright, this is going to have to be replayed. So, this is 0.033 liters is how much we need. Essentially, we need 33 milliliters of solution. Now, if this confused you, you could have also gotten this from M1V1 equals M2V2. I just went ahead and did it the long way. But M1V1, let's redo it. So we got 1 times, our volume is 100 milliliters, and our second molarity is 3, and we don't know the volume. So solving for X gives you 100 divided by 3. And that's how you got the 33. I think I should have gone that route and not worried about the long route. But think about the long route because it allows you to understand this more thoroughly. And now since we have 33 milliliters, what we'll do is we'll first, and you'd have to describe this. That's a flask that needs some adjustment. We're going to put into our volumetric flask 33 milliliters from the burette. That would be step 1. Step 2 then, we would add water. And there's a little mark here. Then step 2 would be adding water up close to this mark. Now, and then you would shake. You would close this, top it off, and then shake. So 3, you would shake it or swirl it for it to dissolve. And then the reason they give us this small dropper is because we want to get as precisely as we can. If you zoom this out, what you'll see is that that neck, that little mark, we want the water level to actually do this sort of thing. The meniscus, we want the bottom portion of the meniscus to be exact, and that we can do using our little dropper. So this is kind of, making sure that we are precise. The other reason you do this is because sometimes when you're adding volumes to different substances, the volume may actually slightly decrease. So you never want it added to the top until you're ready, and you just want to do drop by drop. And that would be the idea. So these steps 1, 2, and 3, and 4, you would actually have to write them out. So go ahead and do that. I'll spare you the agony of doing that. If you understand what's happening, we're good. And then here it says, describe a simple laboratory test that you can use to distinguish between sodium carbonate and calcium carbonate. Now this is actually a very simple problem, very simple question. If we recognize that sodium carbonate is soluble because of the sodium, but calcium carbonate is not because of the carbonate, you could say put a pinch of both into separate beakers. The one that dissolves is your sodium carbonate, because all sodium compounds are soluble. So that's what you can do. You can actually find it through a little solubility test, so watch for these. There are other ways of finding out, but they're probably trying to see if you can pick up the idea of the difference in solubility. You could do, for example, a flame test. You could do a reactivity test that can differentiate between calcium and sodium, but in this case, let's stick to the solution test. Okay, and this should conclude for us this lesson. I'm going to cycle through the homework problems if you don't pick them up from Edmodo. That way you can copy them down. This is extra practice. We're going to have a quiz over this as we did previously. So here are some homework problems. I'll just cycle through these quickly. Pause it as needed. If you don't have these, you can print these out again. Here's some molarity calculation problems for your pleasure. Here's another one. How about a little dilution problem? Here's a little precipitation problem. Here's another one. All good fun. And here's one with some pictures. Always funner with pictures. And here are some free response questions. These are your free response questions. And here's the second one. Okay, so go ahead and work on those, and we will see you in class. This concludes for us lesson 4 of review session 2.